Hey guys, welcome back to Poisson Maths, and in this video we're going to do everything you need to memorise for further stats 1, and I've got this with an edXL focus here. Now I've got this blank version of this PDF. It is in the description for the video, and you can also get the filled in version as well, so you can print out whichever version you prefer, follow along with me, or just have my completed version. Now when you have a look at this whole thing that we've got here, you'll see that the distributions is a pretty big section of this, and there's actually not as much to memorise for the sort of further maths option modules. There tends to be a little bit less, but they go a little bit deeper in terms of the understanding. So you'll also notice for a few different bits I've put whether it's year 2 or year 1. If it doesn't say anything, that means that it is for year 1. So we're going to kick off straight away with discrete random variables and trying to remind ourselves of all of those bits that come from that first chapter. So this is just a very simple one saying the sum of the probabilities. Well, we know that the sum of the probabilities is always going to be 1. This one, if it says FB, it means that it's in the formula book. It's just how do you find the expected value of x. Now, you sum up all of the x outputs multiplied by the probability that x is equal to x, probably something you're very familiar with. So if you're going to do the expected value of x squared, you just do the sum of x squared multiplied by the probability of that value being equal to x. We can generalize this, and this is something that's in the formula book as well, is that instead of it just being x squared, if it was any function, instead of there being an x squared there would be a g of x. So that is going to be the sum of g of x multiplied by the probability that x is equal to x. This variance x formula is also in the formula book as well, but it's a pretty straightforward one to remember if you know it from normal maths. It is the mean of the squares minus the square of the mean. So you do e of x squared and you subtract from it the expected value all squared. These two are not in the formula book. They're to do with coding and about how you might think about how the mean and the variance get affected by coding. Well, if we have ax plus b, we would have a e of x plus b. And the crucial thing to remember for variance is that it's not affected by anything being added on. It's only affected by the multiplication, and it's actually multiplied by a squared. The standard deviation is multiplied by a, but the variance, because it's the standard deviation squared, gets multiplied by a squared. Now, if you ever have any questions where there's like inequalities, you can either actually solve the inequality and use that to find out the probabilities, or you can literally just work out both the x part and the y part and use that to see when it's bigger or when it's smaller. And you probably all know what I'm talking about if you've done lots of exam questions on discrete random variables. So the next part I'm going to drop down to is just approximations. And it says here that if x is a binomial distribution and if n is large and p is small, then we can say that it can be approximated using x with a Poisson distribution with NP. And the reason we can use NP for this is because we know that NP for Poisson is the average. We want that to be the average rates, which would be found from the binomial. The mean for a binomial is NP. I've also said, just to remember, you might need this from the formula book, is that the mean is NP and the variance for the binomial distribution is NP 1 minus p. That's something that could come up, and I've kind of had to throw that in this approximation section because it didn't really fit anywhere that well. Jumping around now to the chi-squared tests that we've got here. This is actually in the formula book. It's in quite a strange section. It feels like it's when you've kind of gone a bit too far. It's at the, looks like it's in the FS2 bit. But this goodness of fit, the x squared that we've got here, this is found by doing the sum of the observed value minus the expected value squared divided by the expected value, and that's in the formula book. But the version, if you've watched my videos, that you'll see that I use the most is where you do the observed squared divided by the expected, you add up all of those and you subtract the total of the observations that there are, so you subtract n. This one's in the formula book, this one is not. This is the one I tend to use the most. Then we've got degrees of freedom that we have here. This is not V, this is nu, it said. What you do is you combine the cells with expected frequencies which are less than 5. So first of all, you have to remind yourself to combine any of them that are less than 5. You then count up the number of cells. You subtract 1 for knowing the total frequency. You would also subtract 1 if you have estimated or calculated either the probability or the constant rate of something. And we call those two things that we've got there the parameters. So when we're thinking about estimating parameters, what you're going to do for this is you will start off by just finding an average from a frequency table. So when you're talking about these chi-squared distributions, you'll have sort of a table of values. That'll be a frequency table. Start off just by finding mu using your GCSE techniques for this. Now for the binomial distribution, this is in the formula book, mu is equal to np. So if you want to find out what p is equal to, you take the mu that you have found and you just divide it by n. So p is just going to be equal to the mu that you've just found, and you're going to divide it by n. For the Poisson distribution, just find the mean from the table. It's the same as lambda that we've got there. For the geometric, because in the formula book mu is equal to 1 over p, well p, if we rearrange this, would just be equal to 1 over mu. So you're just going to find the mean from the table and you'll take its reciprocal, and that will be the value that you've used. And if you ever do have to estimate a parameter, remember you're subtracting 1 from the degrees of freedom that you would use. If we have a contingency table, well, the expected frequency, this will probably make more sense with an example, but as a quick what do we need to memorize, it is our row total multiplied by our column total, and that gets divided by the overall total, which we call the grand total. If we have a contingency table, which is h rows and k columns, well, the degrees of freedom, you just subtract 1 from the number of rows, you subtract 1 from the number of columns, and you multiply them together, and that gives you the total degrees of freedom that we have. Now I'm going to jump over to some year 2 stuff that we've got here, so you can always skip through this if you're only doing year 1. We're talking about the central limit theorem. Now, if we have a random sample of size n, and it is taken from x with mean mu and variance sigma squared, if n is large enough, then approximately x bar is distributed with a normal distribution with a mean of mu and a standard deviation of sigma squared, a variance of sigma squared over n. So it's the same as like what you'd expect for a normal distribution, but we're dividing by the sample size that is being taken. And the something the size of n, the something the approximation, well, the larger the size of n, the better the approximation. So if they've ever got any questions about, how could you improve the approximation, it should be that you can take a larger sample from the distribution. So what's the method for this? You find out mu and sigma squared and the variance. You can do that using any of the kind of methods. Maybe you might have to do something from discrete random variables. Maybe you'll have to do something using some of the stuff that you know about the distributions. What you then do is you write out the x bar distribution using this information, and it becomes a normal distribution, and you just calculate using your normal sort of distribution calculator skills that you've got. Now this is probably the only part of this document where I'm actually going to do a little bit of a question, because this is sort of a bit harder to explain. But if you're doing the central limit theorem and they ask you something about a minimum sample size, I wanted to kind of really critically sort of show you exactly how this should be done. So for example, if after we've applied the central limit theorem, the x bar has a normal distribution with a mean of 50 and the variance is 25 over n, notice it's being divided by n and we don't know the sample size, they've asked us to find the minimum sample size such that the probability that the sample mean is greater than 52 has to be less than 0.05. So the first thing that we do is we standardize it to z, then we can do an inverse normal, and then we can solve for n. So I'll show you what I mean by this. When I talk about standardizing it to z, I want to standardize this thing by changing it all to z. That means it's going to be p of z. Now, instead of it being 52, we will subtract the mean, so it'll be 52 minus 50, and we divide it by the standard deviation. Now, this is the variance, so the standard deviation will be the square root of that, square root of 25, and the square root of n is just going to be written as the square root of n. And we want this thing to be less than 0.05 that we've got here. Then we need to do the inverse normal to find out what would this value be. Now, on my calculator, I'm going to do the inverse normal to find out what would this value be so that it is equal to 0.05. So just grabbing my calculator and just going through and putting in the fact that for the z, it's going to be, the mean is going to be 0, the standard deviation is going to be 1. I will find out what this value is. Okay, and that value is 1.6449. Now we've done that inverse normal, we can see that these two things must be equivalent to each other. And because I want the probability to be less than 0.05, I want this thing to be even further to the right to the right. So I want this thing to be bigger than this part. So that's my last part, is to solve it. So I'm going to make this thing bigger than this thing. 52 minus 50 is just 2. So that's 2 over 5 over root n has got to be bigger than 1.6449. And then sort of doing a little bit of rearranging here that we've got. If I multiply the top and bottom by the square root of n here, I get 2 root n over 5 is greater than 1.6449. I will then do 1.6449. I'll times it by 5. I'll divide it by 2 so that I get that, and then I'll square it so that I get that n has got to be greater than 16.9. In other words, n has got to be equal to 17. Now, I'm wanting to point this out because I don't do a lot of this in the textbook, and this is kind of the method that you would use for this. Another year 2 topic that we've got here are probability generating functions. Now, these standard distributions are all in the formula book, and I don't remember these at all. I would always use the formula book, which is why I've got these filled in pink already, rather than wanting to say, oh, how would we do this? Now, if you're going to do something with probability generating functions, and we were going to prove what these were from first principles, we're going to try and remind ourselves of those 4 methods that we would use to help us get started with this. So for the binomial, you just literally use the binomial expansion formula. That's what you're going to need to do when you're doing this. You're going to use the binomial expansion formula. And obviously you don't just start off with that, it's just like it's going to pop up when you're doing that first principles proving that you've got them. For the Poisson, you need to use the Maclaurin expansion of e to the lambda t. So they're really pulling in all of your knowledge from all across further maths here. We're going to use the Maclaurin expansion of e to the lambda t. Geometric, hopefully you'd remember this one. You're going to use the fact that the sum to infinity is equal to a over 1 minus r. And for the negative binomial, which is probably the hardest one that we've got here, you just have to use at some point in it, you have to use the quoted proof that is below. And it is really, really quite a tricky one. So it might be something that you'd want to review before the exam, just in case they ask you about trying to prove from first principles that this is the formula for negative binomial that we've got. Okay, and we've got the 6 different properties of the probability generating functions that we've got here. Now, the first one is not in the formula book. It's that if you substituted 1 into the probability generating function, it should all sum to 1. Because remember, probability generating functions, it's the coefficients of t that are the probabilities. So it makes sense that the sum, when you sub t as 1, should all sum to 1. This one is in the formula book, and this is what you need to use for first principles. It's that the probability generating function g of x of t gives you e of t to the power of x that we have for this. Okay, and then e of x that we've got here, this one is also in the formula book. This is g dash x, so you're going to differentiate it, and you're going to substitute in 1 for this part. The variance, I'm so relieved this is in the formula book. This is g of x differentiated twice with 1 substituted in. Gx differentiated once with 1 substituted in, and then subtracting from that, g of x differentiated once with 1 substituted in, all squared. So definitely rely on the formula book for this one. The 5th one that we've got is the sums of independent random variables we've got here, and this is in the formula book. If z is equal to x plus y, then the probability generating function for z is just the one for x and the one for y literally multiplied together. Obviously, I'm not teaching you how to do any of these things here. This is just recapping all of that knowledge so that hopefully you know these things before you go into the exam. And for linear coding, this is the one that's not in the formula book. If y is equal to ax plus b, we want to say what is the generating function for y in terms of b? Well, this little, in terms of x, excuse me, this b part that we've got here gets thrown out to the front as t to the power of b. We then have the probability generating function of x here, and we have, instead of t, we have t to the power of a. So the a part, the thing that x is being multiplied by, becomes the power that goes into the substitution for the generating function, and the part that's being added on gets multiplied at the end, and it's all to do with indices, and sort of we explore that a bit when I go through that in those videos. Now, here is probably the biggest bit, and I'm going to go and do Poisson, which is year 1, and then geometric and negative binomial are year 2. So I've got all of the different things I'm going to do along the side. I'm literally just going to work through all of these, okay? So I'm going to start off with Poisson. So from the formula book, we know that x is just distributed. We write it as PO, and then lambda that we've got here. In this particular case, capital X, the definition of it, X is the number of occurrences in a set period. So it is the number of occurrences in a set period. Now that set period could be time or space, so it could be something, how much does it occur per meter squared, or it could be also how much does it occur per hour. Now the outcomes for this is also in the formula book. I really heavily rely on the formula book for further stats 1. They've got that great table that has all of this summarized. The outcomes for this is you could have none, you could have 1, you could have 2, you could have 3, you could have absolutely any of these integers that we've got here. There is no limit. Now, in order for it to be a Poisson distribution, the events must occur, and there are 3 different things that we would need to know. The first one is that they need to occur singly in time or space that we've got here. That means we can't have more than one happening at the same time. The second thing for I, that just means that the events need to be occurring independently. So if you ever need to criticize it, you could say it's unlikely that the events would be independent if you think that's appropriate. And then the last thing is that they need to be occurring at a constant rate. And that constant rate that we have is lambda. Now, if you're going to do these manual calculations that we've got for this actually should have a little FB by it because it is in the formula book. This manual calculation to work out what it is just e to the minus lambda multiplied by lambda to the power of x over x factorial. So it's a nice one to be able to use if you need to, but most of the time you're going to be able to use your calculator for this. For cumulative probabilities, you are literally just going to use your calculator or the tables that are printed for you, because there's a lot of that it's a very calculator heavy section, the Poisson one. Now, moving on to some hypothesis testing, we're talking about p-values here. P-values are where you're finding the probability of a particular thing occurring. So it's saying here if the observed value is x is equal to k, the p-value is the result of that probability that we'll be investigating. So the null hypothesis is that lambda is some constant. Let's say that the alternative hypothesis was that lambda was greater than that constant. Well, all you're going to do for this observation that we've got of k, we're just going to say, well, what's the probability that x is greater than or equal to k? And that's obviously the result of that would be the p-value that you have. If it's less than, it would obviously be less than or equal to k. And I've only done an example here with one-tailed tests. Obviously be aware of the fact that you could have two-tailed tests as well. If you're going to do finding critical regions, I would say the best way to do this is literally to use the tables and to find the bits where you've got it being below that particular threshold that you're looking for. Again, these are in the formula book. Mean is equal to lambda. The variance, which is written as sigma squared, is also equal to lambda. So that's usually a good test if you think something could be a Poisson distribution. This is the only one that's got some extra notes. If x has a Poisson distribution and y has a Poisson distribution, then x plus y, if you were to add those two distributions together, it is still a Poisson distribution, but you just simply add together their rates that you've got. But you can only do this if they are in the same period. So per hour, or per 3 months, or per 6 months, whatever it is, they need to be the same period in order to add them together. Remember, you can always scale them to make that work. Okay, so we're going to do the geometric. I might do the geometric and the negative binomial at the same time as each other, because they do have more similarities instead. So the first thing is notation that we've got here. For geometric, we can say that it is written as geo, and the thing that's the parameter is the probability. Now, for the negative binomial, there are 2 ways of writing this. Neither of them are official, so you probably wouldn't see this ever come up in an exam, but you could use either of them for like the way that you answer things. So you would write neg-bin for negative binomial, and the 2 parameters are r and p. The other way you might sometimes write it is you could just do nb with r and p. Now the difference between these things for the definition is that for a geometric, x is the number of trials to achieve one success. It is the number of trials to achieve one success. So you might be playing a particular game and you want to roll a 6. It's how many times you need to play that game in order to roll a 6. Negative binomial, on the other hand, is the number of trials to achieve r successes. So it is the number of trials to achieve r successes. So in that previous one I just said about rolling a 6, geometric, you want to roll 1 6. You might say, in this case, I want to roll 5 sixes, how long is it going to take for me to roll 5 sixes? And in that case, R would be equal to 5. Now, the outcomes that we've got here, this is the outcome section. What could X possibly be? Well, you can't have 0 for either of these ones, because how could you achieve 1 success in 0 times? So it's actually, for the geometric, it is actually just the natural numbers. It is just 1, 2, 3, etc. And again, there is no limit to this. In theory, you could keep rolling a dice for a long time until you got a 6. Now, for the negative binomial that we've got here, you obviously are trying to get R successes, so the minimum number could be R. You could do R plus 1 or R plus 2, etc., etc. There is no limit to this, but the minimum this time, if you wanted to roll, say, 5 sixes, you've obviously got to do a minimum of 5 rolls in order to be able to get that. Now, they've got really similar outcomes for this kind of stuff. So the conditions where we can do both of these are that they both have got to be independent events. So it's going to be independent for that first condition that we've got there. The second thing is that we've got to have fixed probability. We can't have something where the probability is varying with as the game goes on, or whatever it might be. It's not always going to be a game that I keep talking about here. And then the last thing is that we've got to have 2 outcomes for the particular trials that we're doing. There's either got to be a success or there's got to be a failure. And most of the time, I mean, that's going to be a pretty obvious one, that it's going to just be like, yep, it either I rolled a 6 or I didn't roll a 6. But that's the third condition that we need to have for both of these that we've got here. Now, for the manual calculations, this is for the part where I'm saying if I actually just wanted to find out what is the probability that X is equal to something, both of these are actually in the formula book. So I don't know why I didn't put that these are in the formula book. I will just add that in here. This is in the formula book, and this one is in the formula book too. Just double checking that. Is it in the formula book? Yes, it is. So for the geometric one, we have P multiplied by 1 minus P to the power of X minus 1. And I want to be able to explain this. So first of all, the P is coming from the fact where you have one thing that is successful. That's representing the probability of the thing that is being successful. And then the 1 minus P to the power of X minus 1, this is representing the fact that all of the others failed. And the reason it's to the power of X minus 1 is because we're saying there are X trials that this is being done. 1 is going to be a success, and X minus 1 would be failures that we've got there. Now, I probably would use the formula for this one from the formula book, but I can kind of remember this one, that it's X minus 1 and R minus 1. We then have P to the power of R, and we have 1 minus P to the power of X minus R. Now, the P to the power of R is pretty obvious, right? That is just representing the R successes that we've got. And then this 1 minus P to the power of X minus R is representing the fact that the rest are failures. Now, this binomial coefficient that we've got at the beginning, this is representing the fact that it comes, that it's the combinations for achieving one less than needed. Okay, so this is the combos for achieving one less success than needed. What I mean by that is they could be in lots of different orders. You don't have to have done success, 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 followed by failures. It could be in all different kinds of orders, and that binomial coefficient helps you figure that out. Now, for cumulative, the next part is the cumulative probabilities. Unfortunately, for this part, we don't get given these, and these are the ones that are one of the main things I think you really need to learn by heart here. Now, for geometric, if it's less than or equal to X, we do 1 minus P to the power of X. Now, the way I think about this is actually 1 minus failing to the power of X. 1 minus failing to the power of X, because obviously 1 minus P represents a fail that we've got here. So if I found out the probability that I failed X times, and I do 1 minus that, then that must mean that I must have succeeded in less than or equal to X times that we've got there. If you failed X times, you know you would definitely be taking more than X. So we're kind of flipping it around to going less than or equal to X for that. And if we were doing that X was greater than or equal to X, well, it's going to be 1 minus P to the power of X minus 1. And this is failing to the power of X minus 1. If we think about this, if we fail one less than what we're looking for, then that is equivalent to being successful more than X times that we've got. And I do explain these in a lot more detail if you're thinking, oh my gosh, what does this all mean? but definitely want you to memorize these two that you've got here because they're not in the formula book and they're very important. If you get asked anything cumulative with negative binomial, it must be done manually. What I mean by this is if it was the probability that it was less than or equal to 3, you would have to do a 0, a 1, a 2, and a 3. Well, actually, probably not a 0. You'd have to figure it out in the context of the question and just calculate them individually and add up. I've only seen that come up once, and I think you can do it even using some sums of formulae and stuff like that as well. Critical regions and p-values for hypothesis testing that we've got here again. This is the observed value that is equal to k. We don't do hypothesis testing for a negative binomial, only for geometric. The reason I've included these is because when we did Poisson, the p-values were found with the matching inequality signs that we've got here. But when we do it with geometric, it is flipped and it's the other way round. So if we are interested in the alternative hypothesis that the probability was greater than c, then we would actually expect it to be less than or equal to k. If it was less than c, we would expect it to be greater than or equal to k. The reason this is true is because if you think that the probability of something happening was higher than whatever was stated, then you would expect it to happen quicker. In other words, you would expect the observed value to be lower than this one. And same this way around. If you think that something is rare to happen, you would expect it to take longer, in other words, being greater than or equal to something. The critical regions are also not applicable for the negative binomial. If you had something like this that you were trying to solve to find a critical region, you get to that particular stage for the setup, and then you solve it with logs. So you're going to need to make sure that you know how to solve logarithms for this. These are all in the formula book. I tend to remember these ones, that for the geometric, the mean is just 1 over p, and then the variance is 1 minus p over p squared. I definitely remember this one. This one I find maybe a little bit harder to remember, so I would double check it with the formula book. But these are super easy to know once you've got these ones, because it's the exact same, they just get multiplied by r. So you have r over p, and then you also have 1 minus p multiplied by r, divided by p squared, but it's in the formula book, so I would definitely have that page open for this as well. Last part is a year 2 section, which is quality of tests that we've got here, and it's about the stuff to do with different types of errors, and really this is where they try and pull a lot of further stats 1 all into one place. So first of all, a type 1 error. What is a type 1 error? Well, it's rejecting h0 when it is actually true, because we're rejecting something and we're saying, hold on a second, the thing that we rejected was actually true. Now, the probability of a type 1 error occurring is the actual significance level. It's the actual significance level that we've got here. And this probability of a type 1 error, the actual significance level, is also called the size of the test that we've got. Now, a type 2 error is when you accept h0 when it is actually false. And when you calculate 1 minus the probability of a type 2 error, you get the power of the test. This 1 minus the probability of type 2 is the probability of rejecting h0 when it is false. So type 2 is accepting h0 when it's false. So if you do 1 minus that, it's the probability of rejecting h0 when it is false. Here's the important part. Both the size and the power are both concerned with rejecting h0, i.e. being in the critical region. So when you're being asked anything about size and power, you are going to be doing a lot of work about finding critical regions. And you can see that here, right? 1 minus the probability of a type 2, rejecting h0. Probability of type 1, which is the size, rejecting h0. So they're both associated with being in the critical region. If you're going to do any kind of test comparison, here are some sort of observations around different errors. If you decrease a type 1 error, it actually increases a type 2 error and vice versa. So you can't decrease them both at the same time unless you use this. To reduce both errors, what you can do is by increasing a sample size in whatever the test is that you're doing. You can increase the sample size. Good tests that we're looking for, they have high power and they have low size. We want them to be very powerful And because size is obviously about rejecting h0 when it's true, we want that to be low as well. I haven't seen them ask anything about a power function before, but power function, it basically just shows different powers for different values of the distribution's parameter. And it's pretty straightforward when you actually look at it with some examples. If you do have anything to do with missing sample sizes, it follows the same process as the central limit theorem minimum sample sizes, which was this part that we've got up here. So you do that standardizing inverse normal, and you'll see lots of these horrible fractions within fractions. So be aware that you might be coming up with that as well. Last of all, I had a little bit of space here and I thought, well, what are some of the general tips that we think of for further stats 1? Identify the distribution immediately. Look at the 3 distributions that we've got here, but remember they could also ask you about a normal binomial from normal maths, and they could also ask you about the normal distribution. So identify that distribution as quickly as possible because it will help you as you proceed through the question. Being specific about the Poisson distribution, check the time period carefully for Poisson. It often changes partway through a question and it often changes multiple times, so you need to use your scaling to be able to deal with that. And last of all, you know this, answer all of the questions in the original context that they were asked in. So if they're talking about a particular game that was being played and you're doing a hypothesis test, make sure the conclusion is in the context of the game. If they're talking about people visiting a shop, make sure you're talking about the visitors of the shop and maybe the manager's belief that we have got there. Now, if you've got any other general tips for further stats 1, I would love for you to put them in the comments because, you know, it's not just me and my knowledge of this stuff. You guys have got some really useful tips and these kinds of things. So just to finish off, like I said, go to the description if you want to download this completed version of it, and you can also get the blank version of it too. Well done for sticking through this. I think further stats 1 is an interesting module because there's not tons of stuff to know. It's probably the best resourced one in terms of the formula booklet, and I think that's quite good. Lean on it as much as you can do, okay? Well done, and I will see you soon.